Good morning, everyone. So this will be the presentation for the chapter which relates to the valuation of options in the continuous time framework. So I would like to make a very brief recall of what we did previously. So I will recall you that we did the valuation of options, okay, but in the discrete time framework, okay. So we recall that if we have the timeline like this, we are standing here. So if we are standing here, we have the price of the stock, the underlying stock at time t. And now what happens is that we want the price of the option here. This is something that we do not know. However, we do know the expression of the option here. So here it is a European call option, Euro call. Now, which is a function of st, which is in fact unknown here. So the key question is how to get from here, okay, to here. So in the discrete time framework, we use the binomial tree lattice. Okay, that is, we say that st can go up or down. So here we are relating to up or down, but we know that it is not necessarily up or down. Just have to satisfy this condition where d is the down factor. So this will be std, stu, etc. So this is very important to ensure the no arbitrage principle. So we will be constructing like this. So if this node represents the two possibility of prices, we'll say that it is recombinant, otherwise it will be non-recombinant. So we construct a binomial lattice until reaching st. So we'll be having a set of values of st which will be plugged in here, okay, to have a different set of values for ct. And then how to obtain that c small t here? We use an expression that we related to in the Martingale notation. So this is very important. It is like this: c small t is equal to the discounting value of the expectation of c big T given f small t. Now, I need to draw your attention on two things here. First, f small t is the stock of information. Okay, so I need to point it out that ft is a mathematical tool here. Okay, it is a sigma algebra, sigma field, so it has a mathematical definition. So I'm just giving an indication of what it is. It is stock of information up to and including t. So mathematically it will be defined otherwise. This should be clear to you, but we won't stress on this here. Now, the second thing on which I want to stress on is the risk neutral probability measure. And in contrast to the probability measure P, which is in fact the market probability, the historical probability, which is observed on the market, this probability Q, which is also known to be synthetic, artificial, okay, is in fact constructed to ensure the fair pricing of options. Okay, so now we've seen the Martingale notation here, and that's why you will see that for the continuous time framework, okay, we'll be using that same Martingale approach, but now the only difference is that the construction of st at time small t, okay, up till the time to maturity will be different. We won't be using the binomial tree. In fact, we'll be using the GBM, which is the geometric boundary motion uh, uh, dynamic. Okay, so this is something that we've seen in the previous chapters. Okay, so you will see that in fact, from a general point of view, the procedures are quite the same, but the underlying assumption being changed will also imply a change, an adjustment in terms of the way to reach our objective here, which is the valuation of options. Okay, so here we will be pricing European calls and puts, okay, in the continuous time framework. Okay, so you will see that we've got two approaches. The first one being the Martingale approach. This is what I just explained in the previous slide, and we'll see also a very important result in option pricing, the Blaschko's PD approach. This is very interesting and very important in the world of option pricing. What we'll see here will be very important for will in fact display important tools, very useful tools for the derivation of partial differential equation, even partial integral differential equation in the case where we have jump diffusion processes, okay, to derive these partial differential equation for option pricing. So we'll see that later on, okay. So before going into the depth of the chapter, we need to discuss some technical jargons which will be important in the following slides. So we'll take this as an illustration. So we are standing here. Okay, so we say that the price of my stock is in that state 1. Okay, and then it may go up or down up to state 3 or 2 with the probability is P1 and 1 is P1 respectively. And if it is in 3, then it may go up or down to 7 or 6 respectively with the corresponding probabilities which are written here, P2, P1, P2 and 1 minus P2. Okay, so this is for illustration. Now, the first definition, process, I think perhaps you have come across here this term process in the module stochastic processors. So we understand that a random variable is in fact a parameter which can take different values. Okay, that's why it is called a variable. But in addition to that, the event of taking different values is given by chance. That's why we say that it is random variable. So variable because the parameter takes different values, and that the event of taking different values is given by chance, which that is random. So a synonym to this, it is stochastic. Okay, so it is something like that. At one point in time, I'm observing an event which is random, and then the different outcomes may be associated to random variables. Okay, now if I repeat this experiment, it is just a mere example, at different time instance. Now we have 1 variable, 2 variables, 3 variables, 4 variables. Okay, so that set of variables will form a process because in fact we have added an additional dimension which is time here. Okay, so I think that here this is something that you've come across. So the other things that I'm leaving to you, you can read it alone. I don't think it is important to cover these in the oral speech. So probability measure, I think you understood this. I mentioned that we have the market probability, historical probability versus the risk neutral probability. Okay, so one thing I would like to point out is that we can have different views. Why? Because have ST, I say that ST may go up to UST or UST or DST with the probability P1 minus P. Now, I can have this view, and now another investor may say it is not U, it is U star or D star. So U star, D star are different values to my U and D. And also he may say that his probability measure P is comprises P star and 1 minus P star instead of my P and 1 minus P. Okay, so this will depend on the methodology employed, the data set, the frequency of the data set. Suppose, for example, I'm observing the price of gold over the past year, okay, and I'm taking daily values, and my friend is taking over the same year intraday data. Okay, so for each of the 252 days of the year, he'll be taking, suppose, 1 minute data or 5 minute data. Okay, so for sure, these up and down factors will be different, as well as the probability. Okay, so there are many other factors also that may also influence our choice of UD and probability. But one thing is important, I will recall, is that uh, um, independent of these choices, okay, you will see that the probability Q is the probability that needs to be used for fair pricing of option. Okay, so filtration process. So it is the combination of both histories. Okay, so we'll give some examples here. So at time t is equal to 0, so where we're speaking that we are standing at time t is equal to 0. So f naught is equal to 1 says that at time 0, okay, so this is 1, this is 2. Okay, we are standing here, so for sure we know that we are in state 1. So this is an information that we know. So the set of information is including that we are in state 1. Now, suppose that we are at t is equal to 1 now. Okay, t is equal to 1, we are standing here. So obviously we can be either here or here. Okay, so f1 will be either 1 3 or 1 2. Okay, because at time 1 will be either here or here. Okay, so it will indicate, f1 will indicate whether we have taken this path or this path. Okay, so this is what I just said. Okay, now what is a claim? Now it is different to the process. It is in fact an element of a process. Why? Because it is the set of information that has happened at maturity. Okay, only at maturity. Okay, so it is in fact a function of what has happened at maturity. Here it is, function of the filtration ft. Okay, at maturity, up to maturity and including maturity. So we have here different types of claims. So suppose this is claim 1, claim 2, claim 3. Okay, now x is equal to s2 will be having different values because we are standing here, and this is the modeling of the price of the stock, okay, using a binary tree that I assume. So the first case, when x equal to s2, so my claim is x equal to s2, so the claim can take values 180, 80, 72, 36. This is quite clear, I think. Secondly, x equal to s2 minus 50, so this is implying a call option, European call option, where the strike is K. So pay attention to this plus. So it is the maximum between S2 minus K. and 0. So 180 minus 50, it will be 130. 80 minus 50, 30. 72 minus 50, 22. And then 36 minus 50, it is negative value. So the maximum between 0 and that value is 0, obviously. Now, the third claim, it says that it is the maximum between the values of S node, S1, and S2. Okay, so if we are here, so what is the maximum between these three? So it is obviously 180. If we are here, what is the route to get there? So let me change the, so this is the route. So what is the maximum? Maximum is this, 120. The third route is here, the maximum 80. It is, and the fourth route is also 80. So these are different examples of the claim. So you will understand that it is a function of what has happened up to maturity and including the maturity. So the payoff that we used to employ for the European call option, even for the American call option, is a claim. Good. So it's important to know these jargon and these technical jargon terms. Okay, so conditional expectation operator. So I think that we've been using these, but I think it is important to give some recourse on this. But I consider that you are quite used to these kind of tools. So expectation under Q of x given fi. So I would like to say that when we say given fi, so in French it is sachant que. So given, so knowing that. So we can say that this information is in hand, is known, it is deterministic. So we have all the information that has happened up to and including time I. Okay. For example, expectation of under Q of S2 given F2 is equal to S2. Why? Because I know F2 includes all the information on S up to 2, including 2. So the expectation of S2 is no more, the S2 is no more random, it is deterministic. So I can say it is straightforward here. It is S2. Okay, so F2, now I give more information on the F2. F2 is in fact pointing out that I have used this route. So 1, 3, 7. So I've done this 1, 3, 7. I was in state 1, state 3, and state 7. So expectation on S2, S2 is here. It will be 180. Now, expectation of S2 given F1 is equal to 1, 3. So 1, 3. So I will remove all the annotation here. So it says that expectation of S2 given that we have taken this path, okay, 1, 3. So the expectation of S2 will be a value which will take into account 180 and 80 because we are here. Now, the second expectation here, expectation of S2 given F1 is equal to 1 and 2. So now 1, 2. So it's expectation of S2 given F1 is equal to 1, 2. Now we are here, and then the expectation of S2 will work on 72 and 32. So here we are showing that the filtration, the expectation of S2 given F1, okay, is a very important calculation. Why? Because that F1 is inducing information in that expectation. So knowing that F1 will change the expectation that is working on my S2. This is the example. Okay, so we have expectation of S2 given F1, here also S2 given F1, but the information which is included into the F1 will determine the value which will be calculated. Okay, so previsible process, so it is quite self-explanative. Okay, predictable process is a process which may be determined. Okay, so in advance. So here it is I minus 1, so I'm here. Okay, so if a process is, let's say, phi I, so I'm here, this is the present, and this is the future. I'm here, I'm standing here, and phi I is known, it's deterministic at time I minus 1, where I'm standing, then it says that phi I is previsible. Okay. So it is as if, for example, I'm depositing my money in the bank. I have 100 rupees in the bank. So in 1 year, I know that the bank will give me 3% of savings rate. So the rate of return of my deposit will be 3%. And then this is a fixed deposit. I won't withdraw money from that account. Okay, and I'm assuming also that there won't be any default risk or counterparty risk or credit risk or whatever. Okay, so that 100 rupees that I invest in the bank in 1 year, so I'm standing here, so in 1 year, in 2022, okay, it will be 103. Okay, so 103, which is something in the future, is previsible, predictable at the previous time instant. Okay, so I will recall here the Martingale definition. So Martingale with respect to a probability measure P. So this is important. So we won't be necessarily need require you to define what is meant by Martingale, but you need, however, to understand that a Martingale should be defined with respect to a probability measure. Okay, so without mentioning the probability measure, the definition will be incomplete. Okay, so it is a Martingale with respect to a probability measure P, a filtration Fi, if the expectation under P of Sj, so Sj is found here, given Fi, it is the information that I'm standing here. So I know the present and I know the past. So this is Fi. Okay, so suppose this is 0. So what happens to that expectation? It will be equal to the value of Si. Okay, so I would like to make a kind of illustration that I think is important here. So if I have the set of information here, okay, and I'm standing here, and this is the price Si, I here. Now J is here. J is, let's suppose, 1 day ahead, 1 year ahead, whatever. So I don't know Sj. What the definition is saying is that the expectation of Sj, given that set of information here, that expectation will be equal to Si, donc the value which is here. So I think that from a an intuitive point of view, perspective, we understand that the dynamic, the evolution of the price should be truthless. Because I'm saying that the price here, Sj, the expectation of Sj will be equal to same level as Si, given Fi here. So I'm saying that, in fact, it implies that I should be having something which is driftless. Okay, so perhaps to get it more, to get it clearer here, Perhaps if I give the counterexample, so I have a process like this. Okay, so here it is the price at I, so it is SI. So on the vertical axis, it is no, this is stock price. Okay, now at J, so without considering the martingale approach or whatsoever, so I think that you will agree with me that if I take like the trend, I will say that SJ will be around here. But the martingale says that the expectation of SJ given Fi, donc Fi which is the set of values up to and including the time I, it is equal to SI. So SJ can't be here, it should be here then, same level of, to this. Now, this is quite contradicting that trend that I'm observing. So this is quite clear that for a martingale, we can't have a process with a drift. I think it is clear now. Okay, but we can discuss on that when we'll be doing the feedback on that lecture video. So no worry on this, but I think that this illustration is clear. Now, this explanation leads to this important property of the martingale, which says that the martingale is driftless, driftlessness of a martingale. Okay, so this is what we just illustrated, that we don't have any drift for a process which is obeying the martingale property. Good, so the drift is zero, the mean drift is zero. So if we have a process, stochastic process dx, which is equal to yt dbt, zt dt under a probability measure p. Now xt will be a martingale if and only if, so we have double implication here, x is a martingale, so that x will be martingale with the condition that this is zero. That is, we don't have any drift. So you will recall that the coefficient to dt is the drift. So here, if we want it to be a martingale, it should be driftless. That is the absence of any coefficient to the term dt. Now it has double implication. Is that if I have a process without the drift, a stochastic process without the drift, in the expression of that stochastic process in the SD, then we can say that that process is a martingale. Okay, so let's take, for example, that stochastic process ST is equal to S naught exponential sigma dt minus half sigma squared t, where sigma is the volatility constant, S naught is the price which is known at time t0, and bt is the standard Brownian motion. Now, when we apply Ito lemma to the above, so if we take xt is equal to this, so I think that we will recall that in the Ito lemma that I have given to you, this will be zt and this will be yt. So yt is equal to minus half sigma squared, zt is equal to sigma. Now, when you apply Ito lemma, it is straightforward here, where the function is known to be s naught equal to exponential xt. Okay, so you calculate f dash, you replace in the Ito lemma, you obtain dst, okay, d of that function over x being equal to sigma st dbt. So you will see that there is a coefficient to bt, but we have no coefficient to dt. So here we know that this is a martingale. So this implies that we have this condition being satisfied. For example, I can write this. Good. Okay, so we'll move to the second one, conditional expectation of a claim. Good. So I would like to start with this first. Okay, so you will recall that we have an important property, conditional expectation. Suppose I have this, it is equal to expectation of conditional expectation of x given y. So this can be proven. Uh, Whether you take x continuous, y continuous, or both discrete, or one continuous, the other discrete, whatever. So this is an expression which holds in all cases for x and y being random variable. So now you will see that the same proof to prove this. Okay, I usually prove this in the stochastic processors module in year 2. Okay, that same proof will show that if you take this, for example, given C, for example, so you will have this. Okay, so you can prove this. Good. So you will see that here the expectation of, in fact, the conditional expectation under Fi of the conditional expectation of x given Fj will be equal to the expectation under x given Fi. So if you study this in the light of this, you will see that it is the same. Okay, so given that here we have this result, important result, which is held here, now when we apply it in the case of the Martingale, in fact, when we use this property, we call this the Tower law of Martingale. Okay, good. Now, why Tower law of Martingale? Because I have written this result in the light of the general rule of conditional expectation, from which I have derived this. Okay. Now, when you study this now, okay, what you see is that we have something here, okay, which is given Fj. So it is something which is known at Fj. This part, only this part, it is known at Fj. So as I've said in the module stochastic processors, which I usually teach, okay, but in case I haven't done this module with you, perhaps the lecturer have told you, is that we said that this part, which is in fact a variable in Fj, it is a function in Fj. We say that it is Fj measurable. That is, if I know Fj, I will be able to calculate this. Okay, so this is a function of Fj. Okay, now what happens is that I have something which is in terms of Fj, where j is greater than I, so j is further in the timeline, on the timeline with respect to I. Now, this part is when I take the expectation given Fi on this part, what it gives me? It gives me expectation of x given Fi now. Given Fi. So that variable x given Fj, the expectation of x given Fj, okay, which is Fj measurable, given Fi, what happens? It becomes expectation of x given Fi. Now it is Fi measurable. Okay, so what does this mean is, I think you will understand why when I will recall the Martingale definition. This is Martingale definition. Okay, is that this is a Martingale if I have expectation of fxj given fi is equal to fxi. Perhaps it may be misleading because I'm using the F here. So I will remove that F. Let's suppose it is J, okay, or H. Let's take H here. So H of xj, H of xi. So if I take a function over xj here, given fi, so Martingale, what it says is that at j, which is further on the timeline with respect to I, okay, so h of xj will become h of xi because I'm standing here at I and I know all information up to I. So this is the Martingale definition. So now my h of xj here is this. Then it becomes x of xi. Here it is. So our law of Martingale because I have here the conditional expectation of x given the filtration, which also satisfy the Martingale property. Okay, so don't worry if you go back several times on this part and you are not able to understand what is happening. We'll come back to this in the feedback session that we will be having very soon. Okay, equivalent measures. We say that two probability measures P and Q are equivalent if for any event we have for a given event, okay, that the probability P, okay, over that event E, the occurrence of that event E, the probability associated to this is strictly positive, and they will be equivalent if and only if the probability Q now over the same event E, okay, the probability is strictly positive also. Good. Where PE and QE are the probabilities of E under P and Q measures respectively. Okay. Now, D is displaying a very important theorem here. Okay, so we'll be using this in the following slides. Huh? So Cameron Martin Jezanov theorem. It helps to make the change of probability measures. So we understand that we may be working under P. Now under P we won't be having the no arbitrage principle being obeyed. So this is a problem. So what we do, we need to transit to the other probability world, which is in fact the risk neutral probability world. So how to do that? We'll be using the Cameron-Martin-Jezanov theorem. Okay, so in some books you may find that they relate to this part as being the change of numéraire. Okay, change of numéraire. Okay, so it is used to convert stochastic processes that are not martingales with respect to one probability measure P into processes that are martingales with respect to a second probability measure Q. Okay, so it says that if Bt is a probability is a Brown motion on the probability measure P, so this is notation, and Q is a probability measure which is equivalent to the probability measure P, then there is a F previsible process. So you will recall what is previsible, that if I'm standing at Ft minus 1, okay, at T minus 1, so I know all the information here. The expectation of gamma T given Ft minus 1 will be equal to gamma T itself, because gamma T will be deterministic. Okay. So gamma T such that Bt tilde, so this is a new Brown motion which is being defined here, is equal to the Brown motion under P here. Okay, so that new Brown motion is in fact defined with the probability measure Q now. So we are changing the probability world in order to have the Martingale property being held. Okay, so this is important here. Why? Because as I've said, in our case, we want to have the Martingale property being held, and in addition, we'll be working in the risk neutral probability world. Okay, so the Brown motion under Q, BT tilde, which is equal to BT, which is in fact the Brown motion in the P, probability measure P, plus, okay, the integral of that previsible process, okay, and from time 0 to t, because standing at t. Okay, so we'll see an example. Okay, we have a Brown motion BT here. Okay, now the process xt is defined like this: sigma bt plus mu t. Now you will see that sigma and mu are constant. You see that there is a drift. It is not driftless. So dxt is not xt is not martingale. Now we want to use the CMG to convert xt, okay, to, which is defined with the Brown motion under P. We want to define another xt now, defined with the Brown motion under Q, which this one is not martingale, but this one we want it to be martingale. Okay, so what we do is we use the CMG. Now, how to use the CMG? We need to define the previsible process gamma. So here we assume that gamma is equal to mu over sigma. Now you may ask, how do we determine that gamma previsible process gamma? Okay, so I think when we will complete this part, you will understand how we have deduced that expression for gamma. Now we said that gamma is equal to mu over sigma. We use CMG. CMG says that BT tilde, so we come back to this, BT tilde is equal to BT plus the integral of, so BT tilde is equal to BT plus integral of the gamma previsible process. So when we integrate mu over sigma, it becomes mu over sigma s, so with the limit t from 0 to t, so we get this. Now BT tilde is equal to this. Okay, now I want to define my xt with in terms of BT tilde. So I replace BT by BT tilde minus mu over sigma t. I put it here. So when I replace, you will see that after simplification, I get this. Okay, so what happens is that I have used a previsible process gamma in such a way that I've eliminated that mu. That's why I've been using a mu over sigma. Okay, so if this was, suppose this was A and this was D, so it would have been A over D. Okay, so now I have xt is equal to sigma bt tilde, which is a Brown motion defined under the probability measure Q. Good. So you will see that the expectation under P of xt squared has the drift term raised to the power of 2, so the square of the drift term. But if we take xt squared, we see that it only has the volatility component, and we don't have the drift associated to this. Okay, so I think it is clearer now, in that we use the CMG to convert a process which is defined under a probability measure and which doesn't obey the Martingale definition, the Martingale property. We make a change of numeraire in such a way that we now get a process which satisfies the Martingale property. But this implies a change of probability measure, and this is important for us. Why? Because we'll be using a new probability measure Q, risk neutral probability measure Q, which will help us to reach our objective to have a fair pricing of options. Okay, so let us take now the log normal asset price process. I think you recall this expression. This is something that we've seen in the first chapters, okay, where in fact it is that equation is a consequence of the GBM. This is the GBM, geometric bound motion, which is assumed in this chapter. So we will assume the GBM, the geometric bound motion process here, okay, for what will follow. Okay, so it says that dst, let us put it here. So we remove this part here. dst over st is equal to mu dt, so it is the deterministic component, plus sigma dbt, where dbt is a bound motion. So we know that the bound motion is Gaussian. We will consider a new process now. Dt is equal to exponential minus RT of st. Okay, so perhaps you will see, you will be able to understand why we do this here. Okay, and we can observe it here, because you will see that the mu here is the coefficient to dt, and having a drift here, we don't have the Martingale property being held. So we apply a discounting factor here. We want to find d of dt. Okay, here we have st, d of st. Now we have dt, which is discounting st. We want to have dt, d of dt. So this is the product rule. Okay, simplify, we obtain this. And we see that here also we do have a drift here, mu minus r. Unless we have r is equal to mu, where this will be 0, then we can say that dt is a martingale. Otherwise, we can't say that. So what we do is we want to change the probability measure of the bound motion. So we define an equivalent probability measure in such a way that we have now, as here, to have a bound motion under Q now, which will imply my d of dt being a martingale, so being driftless. Okay, so mu minus r, here there is sigma, so I think we can deduce that it will be the previsible process gamma in the CMG will be equal to mu minus r over sigma. Okay, so bt tilde on the CMG, calculate it, you get this. Now dbt, you make it subject of formula, you get dbt tilde minus this part, here it is. So you have replaced in this expression, and after simplification you see that it is driftless under the new probability measure. Okay, so the expression for st with that new bt, a bound motion bt tilde, you will see it is given like this now. So if you come back to st, so you replace your bt here by the expression of bt. So bt here will be bt tilde minus mu minus r over sigma t. So you place this in this expression here in the exponent. So after simplification, you will see that your mu is removed and replaced by an r here. Okay. So under the risk neutral probability measure Q, new probability measure under which we are working, we are no more working with the drift nu, but here we have the risk-free interest rate. Okay, so this is not a martingale. Okay, it is the discounting value dt, which is a martingale. Okay, good. So we can check, we can verify that Martingale property, so the expectation under Q of dt given du. So you can put it du or fu. Okay, so this should lead to du. D is greater than u. D is further in the timeline with respect to u. So expectation under Q of dt given fu should be equal to du. So after simplification, you will see that this is well du. So we have checked that the CMG transformation that we have applied is well giving dt being a Martingale. So Martingale representation theorem, it says that if I have a stochastic process xt, which is a Martingale under Q, okay, whose volatility satisfies the additional condition that it is with probability 1 always non-zero. So it says that we have a stochastic process here because the volatility is non-zero. Then we have yt being another Q Martingale process. Then we can write yt in terms of xt like this, where dyt is equal to phi or dxt, where phi is in fact a f previsible process. Okay, so we have here xt being a Martingale under the probability measure Q, stochastic process. Y also is a Q Martingale process, so both are Martingales under the same probability measure. So we can write this in terms of each other using that previsible process. Okay, so these are some important properties that needed to be presented to you, which are important tools for what will follow. Okay, now I think that this part you can read it. Okay, you can read this part, but I need to stress on this. When you will read what has written previously, you will see that the price change in the portfolio. So you will recall that we have a portfolio comprising of phi and psi, where phi is the number of units of the stock, and this is the number of units of the bond. Okay, now the price at time t of my portfolio will be phi t st plus psi t bt, because st is the price, unit price of stock, bt unit price of bond, and this is the amount bought in st, this is the amount bought of in phi t. So at time t, I have this. Good. Now at time t plus delta t, okay, I have in fact delta t. You will see that it is the same thing here and here, but the only change is the delta t. So here it is the portfolio composed, built at t plus delta t. Now one thing is very important is that we have wrote it here. It is self-financing. It says that suppose I have a portfolio, so whether this is stock, this is BT, okay, so at time t. Now arriving at t plus delta t, okay, that portfolio perhaps has grown up or decreased a little bit in terms of value, depending on the value of ST or BT or whatever. Okay, so what happens is that there is no ejection or injection of money, in that I'm not closing my position, then take out some money out of it, and then continue my investment without that part of money that I have just removed from my portfolio. No, I don't inject, no eject money from my strategy. So it is the same amount, which is perhaps decreasing or increasing based on what is happening on the market. Okay, this will be clearer afterwards, because I will give an indication in terms of mathematically of what I'm saying, okay, based on the assumption of self-financing. So what happens is that now Vt plus delta t. So this is after at t plus delta t, after building my portfolio. Now, same thing, just before. When I say just before, it is the instant before. I'm speaking perhaps of in terms of fraction of seconds, just before building my portfolio at t plus delta t. What will it be? It will be still my phi t here, okay, st plus delta t. Why it is phi t here? Because it is that amount invested, okay, up to t plus delta t, but just before I'm changing, I am reshuffling my portfolio. So it will be still phi t. St plus delta t is the price on the market at t plus delta t, phi t, psi t plutôt, okay, dt plus delta t. Okay, so I have two prices, okay, in terms of my portfolio, and what I can say is that these two bear the same value because this is just before and this is at the time t plus delta t where I am changing the composition of my portfolio. So why they are same? Because it is self-financing. Self-financing. In that when I have an amount of stock or bond, I'm closing my position is that if I have sold a portfolio, so I buy back. If I have bought an investment, so I sell that asset in such a way that I'm closing all my position. Now, when I see my portfolio, okay, what I do at t plus delta t, I recompose on the portfolio, which will have phi t plus delta t, psi t plus delta t for stock and bond respectively. So it is self-financing. I'm not taking out money or taking in money. So I'm stressing on this. I hope that it is clear for you. So now these two are same. Okay, these two are same. Okay, so Vt plus delta t minus Vt. Okay, so what is Vt plus delta t? It is here. It is this. It is phi t st plus delta t. Psi t Vt plus delta t minus Vt. So what is Vt? Vt is this. So it is phi t, st, etc. Good. Now, when we take delta t, which is the time interval between the two investments, okay, what happens is that when I take this tending to 0, so infinitesimally small time step, so I will be having this being written as dvt and this written as dst and this written as dbt. So I have my change in my portfolio being influenced by the change in the stock price and the change in the bond price. Okay. So this is what I'm saying here, from this to here, is that my portfolio is growing or decreasing in terms of value, not because I'm injecting or ejecting money, but it is changing in terms of value based on what is happening to my stock and to the bond in which I have invested my money. Okay, so the change in my portfolio is dependent on the change of the price of my assets, which is here the risky asset and the risk-free asset BT. Okay, so I think it is summarized here. They say that a portfolio is self-financing if and only if the change in the value of the portfolio is solely affected by the changes in the asset price within it. That is the risky and the risk-free asset. Okay, so this closes this first part of the lecture video of this chapter. Okay, so in the next part we'll be going in the depth of Martingale approach to option pricing in the continuous time. So on the note, I would like to say you thank you for your attention. I hope that the presentation was clear to you. So don't hesitate to go back in the video to see where you have difficulties or issues. And if these difficulties persist, do not hesitate to come back to me. So we'll be having, once again, I'm saying this to assure you that we'll be having a feedback session where we will be discussing the issues of each and every one. So goodbye and thank you.